Today we're going to discuss upper end theory and service. Camshafts. There's a lobe for every valve that's on the engine. There's a lobe on the cams, either single cam or dual overhead cam. There's a lobe per valve. So we have a lobe height that's proportional to the valve lift, and we'll get into that, how that geometry affects the valve action. And on the camshaft, you may have a gear that drives a distributor or an oil pump or both. So you may see a helical gear on a camshaft. Typically, you had them on small block Chevys that were timed to the distributor. And you want to pay attention that that gear is in good condition if you do have one that's on the cam for the engine that you are working on. Cams are typically iron, steel, or hollow. Iron is for older engines. Forged steel alloy is typically what's used in engines. It can't be aluminum. Aluminum's way too soft for the amount of work that the camshaft does, but they can be hollow. There have been hollow camshafts designed to keep the weight down, and you'll see that in both gasoline and diesel engines. Your typical overhead valve camshaft. Well, here we have our camshaft, which is rotating in the block, typically above the crankshaft, driven by a chain or a gear. We have this is showing a hydraulic lifter with a roller. There's going to be oil galleries drilled into the lifter and receives oil through the lifter bore. And if it has that type of lifter, it's hydraulic is going to move oil through the push rod up to the rocker arm. So while the engine's running, you're going to have oil coming out in in small droplets while the engine is running. And here we're taking the motion and we're moving the push rod up while we move the valve down and open the valve. So this is a pretty basic cross section on how this valve operates. So that here it's on a smaller, what's called the inner base circle, so the valve would be closed. As the camshaft rotates around and the outer base circle and the lobe comes into a flank, it begins to push and move the push rod. It's going to move the lifter or cam follower, move the push rod up, and push the valve down to open it. Pretty straightforward. Overhead camshaft. They can be single or dual per cylinder head. And we'll see these in the engines as we take them apart. We're going to have the different types of hydraulic or solid lifters in here. There's a few different styles. One has a replaceable shim to adjust. Those are the solid type. The hydraulic ones are typically self-adjusters. You're also going to see zero lash adjusters also that are in some of the overhead cam configuration. This is your typical what's called a crosshead, where intake air will come into the intake port. The intake valve will open. Now typically in a lot of automotive applications in diesel industrial engines, you'll see the intake valve is larger because the intake air is denser. It has oxygen. In this case, if it's multi-port fuel injected, it will have the fuel injected into on the intake side, so the air charge that's coming in of colder air will have the fuel in it already. If it's a direct injected engine, it's just going to have air coming in, and then the injection and spark will be shared in the cylinder head. But in this case, for this representation, we're just seeing the valve side of this, and then the cam will actuate the exhaust valve, and the exhaust valve will exit the hot burnt gases out of the exhaust port. Here we have a camshaft for an overhead valve engine, pretty common in many V6 and V8 applications and other types of engines. We had the valve train driven off the crankshaft. This photo showing a chain. So if you have 15 teeth on the crank gear, you're going to have 30 teeth on the cam gear. You need 2 rotations here, 720 degrees, for 1 rotation on the cam, 360 degrees. So we have half the speed to give us the full combustion cycle. So the valves will open and close per crankshaft rotation. The valve openings and closings are based on the shape of the cam lobe. We're going to get into that. We're going to get into a diagram there to explain that. This diagram represents how the camshaft actuates a valve and what actually occurs as the camshaft rotates through the cycle. So we'll start up here as we're at the end of the exhaust stroke. The intake valve begins to open and it puts fresh air into the cylinder while the exhaust valve is still open. And that helps, it's called valve overlap, and it helps move and it helps cool the piston, and it helps, since the intake air is denser than the exhaust is burnt air, it's minus the 21% oxygen, it's lighter, hotter, so the colder, denser air will displace the exhausted burnt air. And that happens right here. So the intake valve begins to open, the exhaust valve will close, and the intake stroke will continue to fill the cylinder with air and fuel, typically. And as that passes along, it goes from bottom dead center, it starts moving up to top dead center, compressing the air-fuel charge. As it gets to top dead center, the spark, as it's right before top dead center, the spark will ignite the fuel somewhere around top dead center based upon the engine, and then that will create the power stroke. The power stroke will push the piston down to bottom dead center, and as it gets to bottom dead center, the exhaust valve begins to open towards bottom dead center and continues to stay open past top dead center during valve overlap. So that gives you the whole cycle of what happens in the rotation of the cam and what the valves are doing at each particular time, opening and closing, so that we have the correct intake of air and fuel. We have the valves closed during the compression stroke. We have the valves closed during the ignition and the power stroke, and then the valves open for the exhaust stroke and the intake stroke. So it's pretty straightforward once you see it and you slow it down and understand what the valves are doing as the cam rotates. Lobe terminology. We have a base circle. This is called the base circle here, from this dimension to from here to here. And this is called the outer base circle. They're not calling it, they're just adding the lift. So if you did a measurement from the nose to the heel, and you subtracted the base circle from that, it would give you the lift. So it's another way to do that. This is showing the closing ramp and the closing flank, and this is the opening. So as the camshaft turns, it's going to open, begin to open and open and stay open here. This will be the duration. This geometry determines the duration of the valve opening and filling the cylinder or emptying the cylinder with either intake or exhaust lobe. Here we're showing a camshaft in the block, and here we're showing the cutaway shows the lifter here. It's above the crankshaft. This one is driven by the rear because it looks like we have a flywheel here, so this one is driven by the rear of the at the rear of the engine. So here's your flywheel, and here's your what looks like a cam gear. Camshaft drives for overhead cams. We have sprockets on the camshaft and on the crankshaft gear. So we have a crankshaft gear and we have a camshaft gear. And you can see this one is the crankshaft's obviously half the size of the camshaft. So we have a combination of devices that are driven. Typically water pumps are driven by the timing belt. And we have a idler here that could be spring and hydraulic or hydraulic. And we have the belt has a lifespan, so the OE is going to specify a timing belt service, which should include a water pump service, anywhere between 60,000 to 80,000 for some engines. Some are over 100. The Hondas are 105. thousand, and at that time you want to be replacing all the rotating parts. If it's give the customer the option that you want to be able to understand that the water pump has to be changed, but you also have the belt tensioner, and you have the seals that are below the cam gear and also below the crankshaft gear, and anything that rotates should have those parts changed at that time. It would be a recommended service. Your overhead valve was showing a crankshaft gear with a timing chain. This would have a cover on it, and the timing, the gear will have twice as many teeth on the cam as the crank. This is a camshaft drive that's showing a gear to gear configuration. They are the same. This one is showing straight gears, but it still has the same twice as many gears in the cam as it does in the crank. Here we're showing a chain tensioner that's located on the slack side of the operation. And we need to understand that we have a situation where over time, depending upon how the vehicle is driven, chains can stretch. And also there are instances of chain tensioners failing, and you want to check the technical service bulletins for that particular VIN and see if it has a history of a failed chain tensioner. If not, it's probably going to be okay if we've had the correct frequency of service and we don't have any concerns in the valve train. Here's a variable valve timing, where we're using showing an actuator here that is typically hydraulically actuated. Using overhead cam, overhead valve is going to change the timing, the lift and duration of the valve through the camshaft, and using a actuator with phasing. 3 types of camshaft drives. You're going to write that down and email it to me, right? Thank you. Hydraulic lifters. Hydraulic lifters have there's oil galleries in the cylinder head. If this is overhead cam or overhead valve, it's going to have, both of them will have oil galleries. The oil will go into the lifter and actuate the position and the motion of the cam lobe, and that's going to transfer to the push rod or to the valve, depending upon if it's in the overhead, if it's overhead cam or overhead valve where it's in the block. Okay, solid lifters do require a service to check the lash. So solid lifters, this type looks like it's in the block and doesn't have a adjustment on it, but if it's an overhead cam, it's going to have a shim that's used to change the lash of the valve. But this is pretty basic, what it's showing here. Okay, here we're showing a roller lifter that's going to have a combination of oil, and it's going to have a roller that's going to change position on the cam lobe, which if the engine and the vehicle has correct service, this should last the life of the vehicle because it's always in clean oil. Cylinder heads, cast iron or aluminum. Aluminum is the material of choice this century. Contains your valves, your valve seats, your valve guides, your rocker supports, and upper portion of the combustion chamber. There's coolant and oil return passages in the cylinder head, and it's also designed so that you get the performance that's engineered for that particular application. Here we're showing we're going to have two overhead cams in this particular application because we're looking at 4 valves, 2 intakes, and 2 exhausts. So if this is the exhaust side of the engine here, showing the exhaust manifold will bolt up to this side of the cylinder head, we're going to have a cross flow here, So these will be your intake valves on this side, and this will be your exhaust valves on this side. This is showing a new cylinder head gasket with the fire ring, and if you look carefully, you should be able to see guide pins in here. They would be located at various locations. At least 2 of them are required to keep the cylinder head gasket from moving. You want to keep it on location. Intake and exhaust ports are cast into the head. You have a variety of porting geometries and applications, but since most heads are aluminum, some heads have cross-flow or Siamese ports, so you're going to have the port split into two, so you're going to have a single port with 2 ports coming out in that application. Here's an example of a cross-flow and Siamese heads. We're showing the intake with the Siamese exhaust ports on this side, where we have a exhaust from each cylinder going into the exhaust manifold, considered a cross-flow and Siamese. So we have the diagram down here explains it pretty simply. We have 4 intake ports, and we have the cylinders number 2 and 3 have the Siamese port. Wedge-shaped chamber, spark plug is located at the widest part of the wedge, and in a hemispherical chamber, is shaped like half a circle, and the spark plug is located at the center of the combustion chamber. Now, there's been a variety of these engineering to change the location of the spark plug and try to get the most amount of power and out of that location. So this has been going on for a number of years. A pent-proof combustion chamber used in many modern engines. It's a modified Hemi design, and it's found mostly in engines with 4 valves per cylinder.
The design of the combustion chamber is one of the determining factors when it comes to the overall efficiency and power of the engine. The 3 most commonly found combustion designs in the U.S. are hemispherical, wedge shape, and the heart design. The hemispherical combustion chamber looks like a half of a sphere. The valves are placed on an angle with the intake and exhaust located on opposite sides of the chamber, which creates excellent cross-flow in the chamber and allows the engine to breathe more easily. It will typically have a central spark plug, which means that the flame path has a relatively small distance to travel during ignition, which creates a very efficient combustion process. The hemispherical design is commonly found in smaller passenger vehicles. In the wedge-shaped design, the inline valves are normally tilted away from the spark plug, which is located on the thick side of the wedge, positioned midway between the valves. The relatively steep walls in this design forces the air-fuel flow path downward, resulting in less exhaust. The heart-shaped design is almost oval in shape, and the inline valves are side by side. The spark plug is pointed towards the exhaust of the chamber, which makes for a short flame path and increased power.
Showing the wedge-shaped design, where you put the spark plug has to do with how the flame front of the combustion occurs. So there's a variety of ways to do this, and based on if the engine's a standard production engine or it's trying to get more power and it's trying to get the most power out of each combustion cycle. Here on the Hemi, it's in the center so that the flame front's going to be pretty even across the combustion chamber. They're showing the spark plug location is center here. And the pent roof has the shape of the combustion chamber is a pentagram, and that provides a certain efficiencies when you have the flame front and the combustion occur, because you actually have more pressure here, giving the combustion chamber more power in this particular application. It's pretty common in today's engines that they went to the pent roof combustion chamber. Intake and exhaust valves, they used to be called poppet valves. The British call them that. They allow the air to flow in and out of the combustion chamber. They seal the upper portion of the combustion chamber, and the intake valves are typically larger than the exhaust valves due to the fact that the intake air is colder and heavier, and the exhaust air is burnt air, and it no longer has the oxygen in it, and it's higher temperature, so it'll easily go out of the smaller valve. Valve construction: hardened steel, steel alloys, or stainless. In most production engines, they're going to be steel alloys. Intake and exhaust valves are usually made from different materials because the intake valve operates in a much colder environment. The stem and up to the face of the valve can be a lot cooler than an exhaust valve. They can be one or two pieces, and some are sodium filled, and some in high performance engines and racing engines will use titanium alloys. We have a valve terminology here. We're starting at the top of the valve, where we have the groove that's machined into the tip of the valve for that wedge-shaped keeper that's there that goes into the retainer. So that's what this is showing a representation of. Intake valve stem. We're showing a green for colder air and red for hotter air, and we're showing representing a larger diameter with a taper face and a valve margin, which is the flat. That is very critical dimensions, so you want to make sure that you have specified amount of margin there, or the valve will fail relatively quickly. Here we're showing the valve seats, which are inserts into a cylinder head. They're going to have the corresponding angle, either 30 or 45 degrees, that are dressed into the seat. Valve guides, they support the valve motion up and down. There's a virtually minimal amount of valve clearance that has between the valve and the valve stem. It's going to have just enough room for oil to lubricate the valve stem, and it keeps the valve aligned with the valve seat. So the valve has to be concentric and the valve stem has to be concentric to the valve guide. They can be cast into or inserts in the cylinder head. Here we're showing a valve guide, which is an insert, which is a wearable and a serviceable item. And here we're showing that is just the casting in the integral valve guide is just the casting. And when this wears, the cylinder head has to be completely overhauled. Sometimes if it's high value, they will bore this out and install valve guides. If not, they'll just replace the cylinder head. Typically aluminum cylinder heads, when they get an overheat, they typically are replaced. Cast iron cylinder heads don't have the type of geometry that deforms when they can take more heat than the aluminum ones. So you want to pay attention to what you have, what the materials are, and what is the most likely failure that's going to send a cylinder head out for an overhaul or just a replacement. Valve springs, retainers, and oil seals. When you compress the retainer, you use the magnet here and keep track of your wedges. Your wedge-shaped keepers are specific to this particular engine, so you don't want to be in a situation where you lose a keeper. That could stop the job. Okay, we have an O-ring at the bottom, and we have the spring, and here we have the valve stem and the guide. All of these have to be organized as they come off, per valve, per location, per cylinder. So if you have 2 intake and 2 exhaust valves, you're going to have 4 valves that you have to keep track of exact locations where they came out of the cylinder head. This is critical to keep everything organized so that when you do your assembly, each part goes back to exactly where it came from. This is to make your rebuild successful. If you don't organize your parts correctly, the engine is not going to last. Okay, so now we're showing a diagram here of what we call a rocker ratio. Now, in some engines, we're showing a slightly larger ratio in the pivot point here for the rocker. So it's going to take more force on the cam, the lifter, the push rod to move this valve and open it and close it, so that the distance and the lift and duration that you have is based on this. But they're showing a rocker ratio, that there's less distance between the actuating side of the rocker arm. So that ratio puts more force on this side than it does on this side. So this side has to produce more energy to open and close the valve. Cam followers. There's a variety of cam followers that are out there in your overhead cam engines. They are called buckets, and the hydraulic ones will have an adjustment for lash. Some of these will have shims that go in and will control the valve lash with either a shim, or this one's showing an adjustment. This can be used hydraulically to adjust the valve lash, and it increases the contact between the cam and the valve. But here you have to understand that there are a variety of different cam actuations and adjustments. But here we have, with an overhead cam, we have the camshaft located right at the valve, so we don't have the type of lifter, push rod, and rocker that you would have in a overhead valve. So an overhead cam has far less parts to it, and it's much closer to the valve that it's actuating. Camshaft bearings. Now, in many overhead cam engines, we have an aluminum cylinder head. We have an aluminum bearing cap with hardened steel flange bolts with a specific taper, and the oil flows through the cam cap, and that bore that's machined into the cylinder head, there's oil galleries drilled in there, so it's going to keep an oil flow through the bearing side of the cam, and they generally don't necessarily have bearings in these applications. They increase the oil flow, and it's enough to keep the cam moving clean and without any friction on the aluminum. So it needs to have that oil. So having the correct frequency of oil change and keeping the oil clean will keep this particular application running longer. In engines that get sludge, they're going to create problems with friction in an overhead cam situation like this. So correct frequency of service is very important to the operation of the overheads. Tech A says part of the valve moves through the guide is called the valve face. Tech B says the part of the valve that moves through the guide is called the valve stem. Who is correct? You're going to email me. That's points. Multi-valved engines. We typically started out with 2-valve engines. We have a lot of engines today are 4 valves that will have 2 intake and 2 exhaust valves. We've seen 3-valve engines coming from Japan and from Europe, where we had 2 smaller intake valves and 1 larger exhaust valve. We've also seen 5-valve engines that would have 3 intake valves and 2 exhaust valves. So there's been a variety of utilizations engineered into engines. However, the 4-valve is the most common configuration that you'll see today. Variable valve timing technology controls 3 key characteristics of intake and exhaust valves. The valve timing, the point in which the piston moves and which valves open and close. The valve duration, how long the valves stay open. And the valve lift, how much valves physically open or their opening time. To do this, there's different sensors such as airflow, camshaft, positioning sensors They're going to feed information to the engine control unit, and they're going to use a variety of mechanisms to control the valve characteristics. A Honda VTEC, for example, physically moves the camshaft in order to give the valve more lift. So there's a few different ways that manufacturers do this, but the performance aspects is what drives this feature into valves today. Vehicles equipped with variable valve timing have become commonplace over the last 15 to 20 years. Different versions of variable valve technology exist. Ability to switch the cam lobes within the RPM band to offer valve lift duration and timing to suit various performance needs. Even before engines used a phaser to manipulate cam position and valve timing. The phaser style of variable valve time is common today. They can be found in just about exhaust or both intake and exhaust cams. The alteration of cam position changes the cam center line of the lobe and separation angle between the intake and exhaust cams. This gives flexibility in improving fuel economy and the power while continually to meet the emission standards. Here we see where sensors are monitoring oil pressure, common in variable valve timing engines. The major control component in camshaft phasing is the oil control valve, as a spool valve that operates like those in other hydraulic applications like automatic transmissions. The powertrain control module duty cycles a solenoid that alters the valve position. The overhead valve is a oil traffic control device, and it determines which ports receive which pressure and which are vented. Here we have the BMW Valvetronic system. It works in conjunction with an independent Vano system that continuously varies the timing on both intake and exhaust cams. Valvetronic equipped engines rely on the amount of valve lift for load control rather than a butterfly valve in the intake track. In normal driving, the gas pedal controls the Valvetronic hardware rather than throttle plate. Cylinder heads equipped with this system, the Valvetronic, use an extra set of rocker arms called intermediate arms or lift scalers. They position between the valve stem and the camshaft. These intermediate arms are able to pivot on a central point by means of an extra electronically actuated camshaft. This movement alone, without any movement of the intake cam, will vary the intake valve's lift from fully open, from max power or to almost closed or idle. So this is a system that BMW utilizes, which is essentially controlled by the throttle. Cylinder deactivation is common in today's modern vehicles. They're trying to save fuel and just have enough cylinders active for the power that they need. So how does this cylinder deactivation work? Okay, it basically closes the intake valves which draw in air, and the exhaust valves which release spent gas. It also stops injecting fuel into the cylinder. The piston still moves up and down. It has to, because it's attached to the rotating assembly. So activating and deactivating based on the power needs. General Motors will shut off 4 cylinders in an 8-cylinder configuration to accomplish this. Cylinder head disassembly. In some overhead cam engines, the rocker arms must be removed first, so you have access to the head bolts. Removing the camshaft and keep the bearing caps and follow assemblies in order. Here's a little knowledge check. You could email me the answers. The 2 advantages gained by using variable valve technology systems in modern engines. On to cylinder head disassembly. Measure spring installed height before disassembly. This way you know if everything's assembled correctly, you have your keeper, your wedge-shaped keepers, and your retainer correctly, you're going to have the ability to match the height that was originally in here between the base and the bottom of the retainer with an installed height. So you know what that height is before you continue with your assembly. So if you know what you had before you disassembled it, you have a better chance of attaining that measurement when you do your assembly. Cylinder head disassembly, you could use some tools to loosen the valve keeper. Some people tap them with a soft mallet and a socket. We're using the pneumatic spring compressor in school. It makes it nice to remove the keepers. Just take care and organize all your parts that are coming off. Your retainers, your keepers, and your springs. Those have to be organized per cylinder and valve location. Different types of compressors. We're using this one at the top at school, but in other situations you have to adjust the arms here so that you have clearance between the retainer, the valves, the top of the valve stem, and also your two wedge-shaped keepers. There's a variety of systems tools out there that can control the pressure that you put on the retainer. In this situation, you can slowly put pressure on it and your valve keepers aren't going anywhere. When you use the hydraulic one, it quickly activates, so you have to adjust the reach of the arm so you get just enough compression to expose your wedge-shaped keepers, and you can remove them with your magnet and continue. Cylinder head inspection. Any interference damage between a piston and a valve is typically fatal to the cylinder head, and you can have cracks in the area of the valve guide. Any dent, scratches, cracks, or heat effect should be noted. You want to check the intake and exhaust manifold mount and surface flatnesses with a straight edge. Those have to be perfect. With aluminum cylinder heads, once you have damage in one spot, it's probably time to replace the head. So you want to do a thorough inspection once you have all the components out of the cylinder head. Measure cylinder head warpage in a variety of axes. You need to do this so that you're sure that you have both intake, exhaust, and cylinder head surfaces within specification. If you don't, your ability to gasket and hold the pressures that are necessary won't be there. So you want to make sure that there's no cylinder head warpage, otherwise you could be building an engine that won't last, and you don't want to do that. Aluminum cylinder heads for porosity leaks. Aluminum will degrade from electrolysis. It'll degrade from vibration. It'll fatigue differently than steel. So you want to make sure that you have everything has a good physical look to the surface. The thicknesses, you have to utilize your manufacturer specifications whenever you have anything that has to be a go or no-go in the process. The styles of heads proper for cam bore alignment. So you want to make sure that the journals are sitting in a cam bore that is appropriate for that particular application. Valve inspection. Burnt valve faces, no margin, oil buildup, carbon buildup are all signs of that valves need to be serviced and or replaced. They're showing here a critical dimension here is your valve margin. The margin here has to be a minimum, and will be called out with specification, because if you don't have a valve margin, you're going to have a burn right here at this location where it seals. The top of the valve stem can mushroom, and sometimes you can take a certain amount of material off the valve and you can shim the spring the appropriate amount. But the diameter, the straightness, and the angle of the valve face, all of these are considerations for your valve will have wear. So you want to be aware of where you're looking and what the specifications are for that particular application. Valve seats. Again, heat effect, burning, cracks, and deterioration. Check for any loose seats. Valve seats can sink into the cylinder head further than they should, and seats that need to be replaced if the valve was broken or bent. Valve seats can be pried out if you got to do it carefully and gradually so you don't damage the cylinder head. Okay, retainers and keepers. One retainers will allow the spring to move away from the valve center line. That will affect valve operation and eventually drivability if it's extreme. Valve springs, we have freestanding height, we have squareness, and we have the pressure when the valve is engaged. So those specifications are going to come out of your Mitchell Pro Demand or a manufacturer's platform for that particular vehicle and engine. Here we have our freestanding height, spring closed or installed height, and the spring for C would be with the valve open. You're going to have three different pressure and height specifications here. The deviation, if you have any deviation outside of square, those springs need to be replaced. And we have the pressure that's called out by the manufacturer for valve actuation. We want to make sure that the springs have the correct pressure specification in once they've been actuated. So you go from installed height on the ruler to the actuated height for the valve fully open, and you want to write down your pressure. That's a job sheet that you need to do for that. Inspection of the valve train. Timing belts are typically replaced when the engine and or cylinder head are rebuilt. Check that there's no fluid leaks that can damage the belt. If you have coolant or oil leaking on your timing belt, that could seriously degrade the strength of the belt, and you want to make sure that that's not happening to your timing belt. Timing chains will stretch over long periods of service, so you want to make sure that the belts or the timing chain is within specification. Idler pulleys. In some applications, you want idlers and your tensioners not only checked, but if you have a 100,000-mile service interval with your timing belt, you definitely want to replace the water pump and anything that rotates, including your tensioners and idlers. And also, while you're in there, you should get the seals out of the camshaft and the seals out of the front of the crankshaft, because they're easy to get to, and it only takes a small period of time to get them out and replace them, which is a good practice, and offer that in the service for the customer, that for a small additional fee you can replace those seals on those rotating parts. Gears, sprockets for any wear, breakage, alignment problems. Cam phasers have a testing procedure, and cam followers and lash adjusters. Lash adjusters have to be cleaned, and they have to be typically soaked in some type of solvent and blown out with gentle compressed air, because they have oil galleries in them, and zero lash adjusters, if they're not working correctly, can cause drivability concerns. Rocker arms, the contact point and the oil holes have to be clean. Push rods, you got to check them for oil passage and straightness, so you can soak them in solvent, blow them out with compressed air, and roll them on a flat surface, so if there's any wobble, they're not serviceable. Camshaft and bearings, you got to inspect the lobes and the bearing journals and check the cam for straightness. Typically on a V-block with dial indicators will show you any run out that occurs, and if it's you only have a very small amount of allowable run out on a camshaft, so you want to make sure you're well within specifications, because if it's borderline and you put it in an engine, the engine may not survive very long, and the valve train could have drivability or complete failure. Thorough visual inspection of a cylinder head. Here, where we have the most amount of heat, and the thinnest amount of material is a location that you're going to typically develop cracks first. So you have the end of the valve seat. On each side, this small amount of material here is a place where you're going to see cracks. If it's a ferrous metal, a cast head, you can go in there and clean it and use mag particle, and dye penetrant will also work on both aluminum and cast iron cylinder heads. So you definitely want to be checking a thorough visual inspection of these locations.
Before any work can be done on the cylinder, you'll need to check the valve stems with a micrometer to discover if they can or cannot be reused. If they can be reused, grind the valve tip just enough to flatten it, and then angle and clean the valve face until the surface is nice and smooth. If you notice that the grinding wheel can't make contact with the entire face of the valve, throw it away. It means that the valve stem is bent and needs to be replaced. Once you've made a determination about the condition of the valve and stem, the next step is to check the valve guide, which can typically be repaired by pressing a thin wall of bronze into the head with an air hammer. Once the lining is in place, a calibrated steel broach is driven all the way through the bronze liner, and then any excess liner remaining on the top and bottom is removed. Now that the size of the guide has been established, the next task is cutting the valve seats. Many of today's valve seat and guide machines use 3-blade carbide cutters that allow the operator to cut all 3 angles of the valve seat at the same time. The top and bottom cut, also known as the throat cut, is designed to maintain proper airflow in and out of the chamber, while the middle cut, or seat angle, provides the valve face with a connecting point on the valve seat. The same process is used to cut both the intake and exhaust seats. However, since lower octane fuels cause intense heat and pinging, hardened steel inserts are pressed into the bored-out exhaust seat for added protection. Once the valve work is done, the next step is resurfacing the head. Take the head and place it on a leveling fixture until it's level, and then set it up on a decking machine. Once that's finished, you can begin resurfacing the head, keeping in mind that you should remove as little metal as possible when doing so. The more metal shaved from the heads, the higher the compression ratio, and the closer the valves are to the top of the pistons when they open, which could increase the likelihood of pre-ignition or detonation. Once the head has been resurfaced and thoroughly cleaned, bring it over to a bench and calculate the spring height using a spring height gauge. Spring height is the measurement between the bottom of the retainer and where the spring rests on the head. After these measurements have been taken, the springs are put in a spring checker and compressed to the size of the installed height. This tool will indicate whether the spring is exerting enough pressure to keep the valve properly seated. If it's not exerting enough pressure, you can try using a shim to give it more tension, but if it still fails the test, the spring will need to be replaced. Once you've determined the final installed spring height and have checked spring tension, you can go ahead and install shims, spring seats, and valve seats, followed by the springs, retainers, and keepers.
Resurfacing of a cylinder head. You can only take off a small amount of material removal. Otherwise, there's a lot of concerns. You can have some interference concerns with the piston hitting the valves. That's one item that you have to be aware of. Also, that the compression ratio, there are aftermarket cylinder head gaskets that are thicker that can accommodate a small amount of material removal, but typically 5 or 10 thousandths, or as little as possible. If you get over 20 thousandths, you're now changing the compression ratio, and going more than any known amount that's going to be called out in your specifications, you can have concerns with the interference between the valves and the pistons, so you want to pay attention to that. Removal guides. Resurfacing reduces combustion chamber size, reduces the head thickness, changes the valve timing and may reduce valve to piston clearance, as we just stated. So intake manifolds on V-type engines may not align. So there are concerns when you machine the deck of the block. Valve faces. Valve angle faces and dimensions must be kept within specifications. You must have the correct angle. You can have an interference angle on the seat, the valve insert seat, and you can have a concern with the margin, the valve margin. So these are all required that we take a very close examination of the concerns that are likely to happen in cylinder head service. The valve grinding the face sets the valve lower to the port, so extending the valve stem height. So now we have to shim the spring in order to do that. So the seat may not be replaced. If it is replaced and it's ground, you're going to be changing that dimension, so you chamfer the valve tip after grinding. The valve or the valve seat may need to be replaced if there's an incorrect valve height. You can only cut so much material off a valve insert, and if you get higher than that, you have to put a new insert in order to correct the specification. Valve guide clearance. There can only be a really small amount of material. When you use a small hole gauge, you have to take the measurement in 3 places, because if you don't have the right dimension in there, you're going to have the valve is not going to stay concentric to the seat, and it won't seal correctly, and you can have significant and untimely valve failure, and that is something that you want to avoid. So you have to be diligent and check in all 3 locations in the within the guide with the small hole gauge, and make sure you're within specification. Valve guide problems. Inadequate lubrication will wipe out the valve stem and the guide. Valve geometry problems. If you have a valve that's not perfectly square with the stem, and if you have the wrong stem and guide clearance, you're going to have oil consumption. When you see an engine start up and you have a cloud of blue smoke, you know that you're pulling oil into the intake valve guides, that's for sure. Here we're showing valve guide reamer. You have an insert that you can put in, drive it in. You have a reamer that's going to cut the correct size. That's a known diameter that the reamer has to be cut to that correct specification, and you're going to test it with the small hole gauge when you're done, and you're going to cut off the extra material that's at the top. They're showing the valve guide height. To avoid interference with the valve spring, you need approximately 100 to 100 thousandths of height there. Reconditioned valve seats. Seat must be correct width and correct location. If not, you're going to have a heat transfer problem, and seating pressure reduced on the wide seats, and seats may be ground or replaced. You only have approximately 1 service that you can do to a valve seat insert. Measuring seat width. You have a scale that you have to have that width, otherwise you don't have enough material there to seat the valve and have enough material to handle the heat effect from the combustion. Valve grinding. There's a small amount of interference that can be cut over and above the initial 45-degree angle.
Valve seats are hardened and are often pressed into a cast depression. Valve seats are sized to match the valve shape, and when it comes into contact with the valve face, provides a leak-tight seal. Seats for cylinder heads are typically made from an iron alloy. Valve faces are ground at 30 and 45-degree angles, depending on the engine. The intake and exhaust valves rest on the seat, which is typically ground to the same angle as the face. However, they can differ. For example, resurfacing the face at 45 degrees and the seat at 46 degrees. The difference is called an interference angle. An interference angle allows for expansion between the valve face and seat of a new engine.
Checking valve fit. You could use Prussian blue. You can see what you get when you put the valve open and closed against the seat, and see if you have any gaps in the bluing effect. And that's an inspection pattern with the die, so you want to see an even pattern of blue distribution from the machinist blue to between the two surfaces. Valve lapping is another way to you can remove any of the small imperfections in the contact area from the cutting tool. This is important. You can also use lapping compound to see how your fit is going to be between the valve and the valve seat. So the valve face and the valve seat can also be examined by the pattern of the lapping compound when you rotate it with the suction cup tool. Valve stems typically are replaced at every overhaul. You have different styles, but you have to have, they only allow a small amount of oil to coat the valve stem. And if these are not working correctly, they're going to allow oil to get into the combustion chamber, and they're only going to wear out. They're not going to work correctly. Knowledge check. Valve seat that is too narrow may cause insufficient watt to transfer from the valve to the head. You can email me the answer. Assembling of the cylinder head. You got your installed stem heights and installed spring heights have to be checked, and as you install each valve. The stem height affected by the valve and the seat, and valve spring height may be adjusted using shims. Typically, shims will come in 5 and 10 thousandths increments. You may have a spacer style that may be up to 20 or 25 thousandths if you had that much material removed. Assembling overhead cam heads. Cam full round inserts are pressed into the head. Don't use overhead valve cam bearing tools when you're doing overhead cam heads. Some overhead cam engines do not use insert bearings. They're just going to use the oil that flows through between the bearing cap and the bearing bore and the cam journal. Coat all rockers, adjusters, push rods, lifters, and other parts with oil for assembly, and adjust the valve lash and install the cylinder head.
After an engine block has been disassembled and prepped for rebuild, the next step is installing the cam bearing. Begin by placing the bearing on a rubber mandrel, and then insert the mandrel into the block and tap the bearing into place. When working on overhead cam engines, the majority of them use a one-piece balance shaft bearing instead of cam bearings, so installing the camshaft becomes a much simpler process. On an overhead cam, the first step is reinstalling the hydraulic lashers and rocker arms. Next, place the camshaft in the block and then lubricate the cam lobes. After that's finished, install the bearing caps, keeping in mind that each one has to be placed in its proper position. Once in position, each cap is hand tightened with a socket wrench. The ring seal and timing sprocket are installed next, and then the caps are torqued to specification. Once installation of the camshaft has been completed, the lobes are lubricated a second time. On a standard cam-in-the-block engine, the camshaft is placed into position with an installation handle, which is used to gently slide the camshaft into the block. You should make sure not to damage or dislodge any bearings during this process. Once installed, the camshaft should rotate freely.